Okay, so let's recall that in the last few graph theory videos, we were discussing the cycle space of a graph, which is a subspace of the edge space. Precisely, it's the subspace spanned by all the cycles. Now, today we are going to see another subspace of the edge space of a graph. So, let's start. If V1 comma V2 is a partition of V, where V is of course the vertex set of a graph, then the set E V1 comma V2 of all the edges of G crossing this partition is called a cut or co-cycle of the graph. So let us recall that if we are given a graph like this with vertex set V and edge set E, and say we have two, so this is the vertex set V, in it say we have two subsets, say E1 and E1 looks a little confusing because by E we generally mean edge. So let's call this U1 and another subset U2. Now let's recall that among all the edges that we have in G, there may be some edges whose ends will lie in U1 and U2. That is, one end will lie in U1 and the other end will lie in U2. Now the set of all those edges whose ends lie between U1 and U2 in this way, we have already denoted that set by this notation. In the very beginning of our graph theory in this book, we have already come across this notation. So here what we are having is not just any two subsets V1 and V2 of V, but they form a partition of V. That means V1 and V2 are both non-empty subsets of V, their union is V, and their intersection is the empty set. That means they do not have any common vertex. In that case, this set, which we say crosses this partition, that is the set of all edges that crosses this partition, it just simply means that we have edges like this. So for this special case, the situation is like this. So this is our V, and this is V1, this is V2. So the set of all edges with one end in V1 and another end in V2, they are being considered, and that set is said to cross this partition. It's just a way of saying that this is the situation. Is called, such a set is called a cut or co-cycle of the graph. Okay. Recall that for V1 equal to V, the set of all edges crossing the partition or let us show it explicitly, because in this case V1 is this special, it's a singleton set, it has precisely one vertex crossing this partition is denoted by E of V, which is also something we have already seen, and this is nothing but the set of all edges at the vertex E. That means, say this is our V, so it is the set of these edges. Whatever edges we have in G that are incident with this, or rather this vertex is incident with all those edges, so they are being collected together and their set is E of V. Note that this is obviously a special case of this, because in this case one partition set consists of this single vertex V and the other one obviously consists of the remaining vertices. So edges between V1 and the rest V2, which is obtained from V by removing this single vertex V. Okay, now with this understanding, with this definition of cuts, we are going to see the next result, that the set of all cuts in a graph along with the empty set that is a subspace of the H space of a graph. So that is this next result, proposition 193. And the statement is this: together with the empty set, the cuts in G, the cuts in G form a subspace of epsilon of G. The cuts in G form a subspace which we denote by C star of the H space of G. So that is one thing we are claiming in this proposition, and there is something else also. This subspace is generated by cuts of the form E of V. This subspace is generated by the cuts of the form E of V. Okay. Now, before we start writing the proof, let us also note the slight difference between the cut space and the cycle space, which we already saw in the previous videos. Of course, actually they are different subspaces, but The difference that I want to draw your attention to is this. Remember that in case of cycle space, the cycle space was the subspace of the H space spanned by the cycles. So the cycles form a spanning set for the cycle space. Here, however, the cuts themselves form a subspace. Of course, they also span a subspace, but the collection of cuts along with the empty set itself is a subspace. And here, in this case, also we can find a spanning set, just like the cycles form a spanning set for the cycle space. In this case, in fact, that is the second part. This subspace is generated by means spanned by the cuts of this form. Okay, so let's now try to show this. Now, in order to prove that this set is a subspace, what do we have to do? We have to show that it is closed under the formation of sum of two vectors in the H space, and that's just it. But why is that so? I mean, if we have, say, a non-empty subset E, let me call it E prime, because actually E denotes the entire H set of the graph. Let E prime be a non-empty subset of the H space. Suppose we want to show that E prime is a subspace of epsilon of G. Simply, if you just apply the subspace test on this subset, what do you know from linear algebra? It is just this, that if you take two elements, that is two vectors in E prime and also one scalar from the underlying field, we know what the field is, the two element field, but just simply saying how one should proceed for showing this. So what is it that you have to show? You have to show that E1 plus E2 belongs to E prime. This is one thing. And the other thing is that lambda times E1 should belong to E prime. If you manage to show these two things, then that just simply means by the subspace test from linear algebra that this is a subspace of the H space of G. Now we know that our underlying field of scalars is the two element field. And because of this, we need not even bother about this part. Why? That's because if we multiply a vector by 0, then from the elementary properties in any vector space, this is going to be the 0 vector. And our 0 vector actually is the empty set, but that's not the point here. So we are going to get the 0 vector, which anyway belongs to E prime. Why? Because as I said, our 0 vector in the H space is the empty set having no edge, and this already is in our set of, I mean the set that is given here. Let us call that also E prime. And if we are choosing E1 from E prime, then 1 times E1 is again by, in fact, the fourth vector space axiom itself, this is E1. So this belongs to E prime. So we need not even bother about this, showing this second part of showing that a subset is a subspace. So we should concentrate on this, showing that the sum is again in E prime. So let us now start the proof. And we are not even going to mention, in fact the author has not mentioned that only that needs to be shown, that the set is closed under the formation of sum. So this is how the proof starts. Oh, I was calling it E prime, but we already have called it something, no? C star. Let C star denote the set of all the cuts of G. The underlying graph G is always there in the background, along with the empty set. Let D and D prime be two such cuts. Note one thing very carefully. In order to show that a subset of a vector space is a subspace, you have to first of all make sure that it's a non-empty subset. If you have the empty subset, you cannot do anything with it. Our C star is non-empty. We don't really know whether G has cuts or not, or whatever the situation is. That depends entirely on what G is. And because our G is just simply a graph G, we don't actually know about cuts. However, the empty set is in any case in C star, because that's how C star has been defined. So C star is actually a non-empty subset of the H space. Okay, now there we have considered two cuts, D and D prime, which are vectors. Now there are two very simple situations in which D plus D prime is going to be in C star again. So let's handle them first. If D is equal to D prime, then D plus D prime is equal to D plus D. But you know that in our vector space, every element is its, the negative of every vector is itself. Every element is its additive inverse in the group in the vector space under summation. So this is the zero vector, and our zero vector is the empty set, and that belongs to C star. So in this case, at least, yes, the sum belongs to C star. There is another case like this. If say D prime is itself the empty set. Actually here I should not have said that these two are cuts. These two are just elements in C star. Each one of them may be a cut or maybe the empty set also. So now let us consider one such situation where D star is empty. D may or may not be empty. We are not bothered about that. If D star is empty, then also the sum can be calculated very easily. Then D plus D prime is equal to this, and since in our H space the empty set is the zero vector, so this is D, which again of course belongs to C star. So in these two cases, and you can understand that a similar situation occurs if D is empty. So now we can assume that D and D prime are both non-empty, that is they are both cuts, legitimate cuts, and also that they are distinct. We now assume that these are distinct and both are non-empty. Non-empty means they are cuts according to that first definition. So if both of them are cuts, then corresponding to them we will have partitions for the vertex set of the graph. Let v1 comma v2 and v1 prime comma v2 prime be the partitions of our vertex set V corresponding to, I think this is how far I can write with this marker. Let me now use the other one. I need to replace this one, but I am not getting the time. Partitions of V corresponding to D and D prime respectively. Okay, now we want to prove that D plus D prime is also a cut. That's what we want to show. So that means if we take the sum of D and D prime, where we know what we mean by sum, for us some vector addition in the edge space means symmetric difference of two sets of edges, because after all these are sets of edges. Remember, each cut is after all a set of edges. Crossing a partition, that thing is there, but after all each one of them is a set of edges. So actually they are vectors in the edge space, because otherwise this whole thing does not make sense. So when we take the sum of D and D prime, what is it that we are doing? We will look at the set here and the set here. Each one of them is a set of some edges. We will then see whether we have any common edge or not, whether there is an element in their intersection, and then we are going to remove the intersection from the union. So that will give us the symmetric difference, and that is the sum. Okay. Now we want to prove that this sum is also a cut. That means corresponding to this sum, this set of edges, there is a partition of the vertex set which is crossed by the edges of this set. So for that there is a diagram that is given, and in fact something else is also written. Then D plus D prime consists of, this of course it will be the case. Then D plus D prime consists of all the edges that cross one of the partitions but not the other, because if an edge in D plus D prime crosses this partition as well as this partition, then that means it belongs to both D and D prime. But such edges are not allowed since we are taking symmetric difference. Edges that cross, exactly how is it written? One of these partitions but not the other. Okay. Consists of all such edges, all the edges that cross one of the partitions but not the other. And now there is a little diagram to show the situation. And the diagram goes like this. This is considered as the entire vertex set, this egg, and there is one partition of this, and another partition. You have to understand that this diagram is in no way an actual diagram of our graph. It just shows what the situation is. So this is the vertex set V, the entire vertex set, and this line divides V1 from V2. So say you can consider this side as V1 and this side of the vertex set as V2. But simultaneously we have the other partition also, and that is given by this horizontal line. The upper half is V1 prime and the lower half is V2 prime. Now, what sort of edges are allowed in D plus D prime? This type of edges are not allowed. I mean, one edge whose one end lies here and the other end lies here. That is not allowed. Why? Because if you have such an edge, then its one end is lying in, am I saying it correctly? If I have an edge whose one end lies here, then it belongs to V1 intersection V2 prime, okay? And the other end is lying here, which means that the other end belongs to V2 intersection V1 prime. But then what is the problem? Why did I say that we cannot have an edge like this? I got confused. Oh, because, okay. Yeah, now I understand. Suppose you have an, let me draw it somewhat like this so that I can erase it quickly. Then this edge crosses the partition V1 comma V2. Why? Because one end lies in V1 and the other end is lying in V2, but at the same time it is also crossing the other partition V1 prime comma V2 prime, because one end lies in V1 prime and the other end is lying in V2 prime. But then this becomes an edge that is in the set D as well as D prime, but we do not have such common edges in the symmetric difference of two edge sets. So that is why this type of edges are not allowed. Also, this type of edges also are not allowed for a similar reason, because then one end belongs to again V1, the other end belongs to V2. Also, one end lies in V1 prime and the other end lies in V2 prime. So that means the edges that are allowed are either like this or this. So let's now carefully wrap this thing up and draw the allowed edges. some such edges have been shown in the text, so let me draw accordingly. This is an allowed edge, allowed in this thumb. This is also an allowed edge. We may have two like this. And actually we can have adjacent edges also, like these two. Let us also see whether these are really allowed or not. This edge crosses the partition V1, V2 because one end lies in V1 and the other end lies in V2, but it does not cross V1 prime, V2 prime because both of its ends lie in V1 prime. A similar situation is there for this edge, and these edges, these four edges cross the partition V1 prime, V2 prime because they are literally crossing. No, they are coming from one side, one set in the partition, and to the other set of the partition. That's why I think it's called, the edges are crossing the partition. So each one of these four edges crosses the partition V1 prime, V2 prime, but none of them crosses the other partition because these two edges have their ends, all of them lying in V1, whereas here all the ends are lying in V2. Okay. So now after this line next comes, but these are precisely the edges. So that means now we have to mathematically express the allowed edges, but these are precisely the edges between these sets. V1 intersection V1 prime, that means this one, V1 intersection V1 prime union V2 intersection V2 prime, that means this means actually the common thing. Let me first write and then I will see what is it that we have in the figure and try to match it with this one. Between this set and V1 intersection V2 prime union V1 prime intersection V2. Let's see, does it make sense? So what we are saying is that all the edges that we will come across in D and D prime considered together, from among them we will leave only those that are between these two vertex sets. Let us consider this edge, for example. One end lies in V1 because it's on this side, as well as V1 prime because it's above this horizontal line. So it belongs to V1 intersection V1 prime. And this other end lies where? In V2 intersection V1 prime, or the same thing, V1 prime intersection V2. V1 prime intersection V2. So this edge is like this. What about this edge? One end lies in V2 prime intersection V1, that means this one, and the other edge lies in V2 intersection V2 prime. Okay, let's see the other edges also. From these two, it's enough to consider only one. Say this one. One end lies in V2 prime intersection V1. V2 prime intersection V1, that means here, and the other end lies in V1 intersection V1 prime, that means here. So luckily we have written these two vertex sets in such a way that here itself we can see the edges. And what about one of these two edges, say this one. One end lies in V2 prime intersection V2, that means here, and the other end lies in V1 prime intersection V2. V1 prime intersection V2. Yes. Okay. Fine. So the edges that we have in this sum cross these two sets, but still we have something else to show, and this something else is going to be a little large somewhat. Namely, we have to show that these two vertex sets now form a partition of V, because then only the edges in this are crossing a partition of V, and by definition it will then be a cut. So now what we are left to prove is that these two sets form a partition of V. Now we show that. Because the individual sets look somewhat complicated, so we need to carefully show everything, that each one of them is non-empty, their union is V, and their intersection is empty. Okay, so we start by supposing, let's say the first one is empty actually, and we will expect to derive a contradiction. This is union V2 intersection V2 prime. In these unions, intersections, the sets and their primed versions, it's very easy to get confused. So you have to be extra careful. Suppose this is empty. Now a union of two sets is empty, that means both of them have to be empty. Then V1 intersection V1 prime is empty, and V2 intersection V2 prime is also empty. Okay, but we also have, keep in mind that V1 and V2 form a partition of V, and so do V1 prime and V2 prime. So we additionally have these things. V1 union V2 is equal to V, which is equal to V1 prime union V2 prime, and also that these intersections are empty. Okay. Now, do you remember that we were given that the cuts D, we assumed that the cuts D and D prime, corresponding to which we have these two partitions, they are distinct. D is not equal to D prime. So we are going to now use these things and show that D is equal to D prime. So that would be a contradiction. Now let phi be a vertex in V1, say. Then phi belongs to V1 union V2. Naturally, if it is in V1, then it will be in the union. But that is equal to V1 prime union V2 prime now I think before proceeding like this, I should assume something else. No, not okay. So that means it will not match with whatever I have written here. Anyway, forget about what I was saying. So we have this condition that V1 and V1 prime are empty. Okay. Now we have chosen an arbitrary element V in V1. So that means I don't need this. So now V belongs to this, which is equal to this. This implies I won't need the figure also. Now it is just basic set theory. This implies V belongs to V2 prime. But why V2 prime? Why not V1 prime? That is because these two are disjoint and we have chosen V from V1. So V cannot also simultaneously possibly be in V1 prime. That is not possible due to this disjointness of V1 and V1 prime. So within brackets we can write since this. So what we have shown is that V1 is a subset of V2 prime. Okay. Now we want to show that the reverse inclusion is also true. So for that, let Y be, and we chose V. No? Actually, you can write anything, but just for the sake of I don't know what, let me call this U. Let U belong to V2 prime. Then U belongs to V1 prime union V2 prime, which is V1 union V2. So U belongs to V1 or U belongs to V2. Okay. Our aim is to show that U belongs to V1. So suppose that U does not belong to V1. Okay, then U belongs to V2 because that is the only option now. Now keep in mind that we have this condition also. This one we have already used. Now it's time for us to use this one. Since V2 intersection V2 prime is empty, this implies that because u belongs to V2, it cannot belong to V2 prime. Okay, but that is a contradiction because that is where actually u is coming from V2 prime. So that will give us a contradiction. This implies u does not belong to V2 prime, a contradiction. So our last supposition is wrong, i.e. This supposition, that means u has to belong to V1. Hence V2 prime is also a subset of V1. So we have proved, now you combine these two containments, combining them you get equality. This implies V2, which is V minus V1. Why is this? Why is V2 V minus V1? That is because V1 and V2 form a partition of V. So if so the complement of each one of them is the other one. That's just it. But now that is V minus V2 prime, which is equal to V1 prime. Again, because V1 prime and V2 prime also form a partition of V. So we have proved that V comma V2, I mean V1 is equal to V2 prime and V2 is equal to V1 prime. Thus, this is equal to this. i.e. D is equal to D prime, which itself is a contradiction. So that means our supposition is wrong. What was our supposition? I forgot. Our supposition was that that set is empty. That thing was our supposition. So, and what was our set? V1 intersection V1 prime union V2 intersection V2 prime, it cannot be empty. It is non-empty. Now before we proceed with the proof, before we continue the proof, let me tell you something about the logic. In this kind of proofs, often when we find something difficult to prove, we just suppose that the negation is true and arrive at a contradiction. At one point we supposed that this union is empty, and now we have arrived at a contradiction, and that makes us conclude that okay, that is not true. The union must be non-empty. But do you see that within that supposition we have again supposed something else? So it's a supposition within a supposition. Now here also you are trying to derive a contradiction. When you suppose things like this in a nested manner, that is one supposition under another supposition, always make sure that first you get the job done here itself and get rid of this inner supposition, and then only you go to the outer supposition. Because if you don't do that, then your everything will get messed up. So here we supposed something within that supposition, and here we proved that this inner supposition is wrong, and so we obtained what we wanted to obtain. And then we then continued and proved that the outer supposition is wrong, and hence that first supposition also must be false, so its negation is true. Just wanted to say that. Okay. Now similarly, one can prove that the other set, which is V1 intersection V2 prime union V1 prime intersection V2 let me again see if I have written it correctly. Here with V1 I have taken V1 prime, here with V1 I have taken V2 prime. So with V1 prime I am taking V2, or rather with V2 I am taking V1 prime, there I took V2 prime. Okay, so this is also non-empty. Our next job is to show that taking the union of these two sets I get V. For that, let phi be any element in phi. Then phi belongs to V1 union V2, and since V1 and V2 form a partition of capital V, and at the same time V also belongs to V1 prime union V2 prime. Okay, so V is either in V1 or in V2, and simultaneously V is either in V1 prime or in V2 prime. Now the four cases will arise. If V belongs to V1 and V belongs to V1 prime, then V belongs to their intersection. This is one case. Then if V belongs to V1 and V belongs to V2 prime, then V belongs to their intersection. This is the second case. Then third, I think you can now see how the union of this and this is the entire vertex set V. If V belongs to V2 and V belongs to V1 prime, then V belongs to V1 prime intersection V2, and finally if V belongs to V2 and V belongs to V2 prime, then V belongs to the intersection of V2 and V2 prime. So that means either V belongs to this, where did it go, this one, or V belongs to V1 and V2 prime, that is this one, or V belongs to V1 prime and V2, that is here V will be, or V belongs to V1 prime intersection V2 prime, that is here. That means any vertex belongs to either this union or this union. So the entire vertex set V is itself a subset of the union of these two unions, but the individual sets themselves are already subsets of V, so their union is a subset of V, so that's why V is equal to the union. Hence V is equal to V1 intersection V1 prime union V2 intersection V2 prime union V1 intersection V2 prime union V1 prime intersection V2. So we have also shown that the sets in question, when you take their union, you get the entire set V. Now there is one more thing left to show, namely that their intersection is empty. So without writing anything more unnecessarily, let us suppose there exists an element Z or Z belonging to the intersection of these two sets, this set and this set. If you want, you can show that this is equal to V without using elements, that is just by using properties of sets. Maybe you will be able to use distributive clause or union and intersection, those things you may be able to get this same thing. I don't know because I haven't seen it that way, but you can try. I haven't tried that way because there are so many unions and intersections involved now, so I thought it would be better to consider elements. Okay, then union V2 intersection V2 prime, and this belongs to so or we have to be careful with these ors and ands, so we have to use brackets as many as we need. This and V1 intersection V2 prime, or keep in mind this is or because here we have union. so now what we have from this situation, we are going to have 4 cases, or let's proceed like this. If our vertex belongs to V1 intersection V1 prime, then it belongs to V1 and V1 prime. Now because V1 and V2 are disjoint due to them forming a partition, our vertex cannot simultaneously belong to V2. Similarly, because of this thing, our vertex cannot belong to V2 prime. Since these two are disjoint and so are V1 prime and V2 prime, we have our vertex not belonging to no, what am I writing? There won't be any 1 here, and it also does not belong to V2 prime. Okay. Now if our vertex does not belong to V2, then obviously it cannot belong to the intersection of V2 and V1 prime, because this is a subset of V2. If it is not inside V2, then how can it be inside the smaller thing naturally? So that means Z does not belong to this set. Similarly, because our vertex does not belong to V2 prime, it also again does not belong to this. So Z belongs to neither V1 intersection V2 prime nor V1 prime intersection V2, i.e. it does not belong to their union. And that is a contradiction that contradicts this thing. This is a contradiction. A similar contradiction arises if we assume that Z belongs to this, because this one has arisen from assuming that Z belongs to this intersection. If you assume the other thing, then also you will get a contradiction similarly. So that means none of them can be assumed, which in itself is a contradiction. Thus we have arrived at a dead end. So our you can write last supposition. It's always good to write last supposition. That is because just I said, like I said previously, that when you suppose something, you first get the job done there itself. So you got rid of it. So anytime you are dealing with suppositions, even if you are taking nested supposition within a supposition, within that another supposition, always when you are towards the end of saying or concluding that your supposition is wrong because of this contradiction, it's always the last supposition. So our last supposition is wrong, i.e. no such vertex exists, i.e. the intersection is empty. Intersection of what? V1 prime intersection V2 union V1 intersection V2 prime. This intersection must be empty. Hence, the sets form a partition of V, which, in order to again bring back those things, which the edges of D plus D prime cross. So D plus D prime, finally we can now say that it belongs to our set of cuts along with the empty set. Hence, this is a subspace of the edge space of our graph. But the proof is not over yet. Recall that there was a second part of the proof. We now need to show that each cut is actually generated by, or rather you can also say that that this subspace is spanned by or generated by cuts of that special form E of V. And for that, this second part is not very big. It's 2 or 3 lines. So let me copy what the author has written, our second assertion, and then we will try to understand what Diestel means. That the subspace C star is spanned by or generated by the cuts of the firm E of V follows from the fact that each edge xy in G lies in precisely two such cuts. And they are these in E of x and in E of y. So any cut or any vertex set edge set of this form E of v1 comma v2 is expressible as summation E of v as v varies over v1. Now we need to understand how exactly is this equation true. Okay, how is it coming? For that, let us, and this is where the proof ends. Now before we show that how this equation is true, let us see what we have written. Our second assertion that the subspace C star, that means our second assertion that the subspace actually is having the set of this type of cuts as a spanning set. That assertion follows from the fact that each edge in our graph belongs to precisely or lies in precisely two such cuts. One is E of x and the other is E of y, where x and y are the ends of our edge. And that is why this cut is expressible like this as a sum. And note that what have we achieved here? We have shown that this general vector, this cut in our subspace C star is a sum, means a linear combination, also you can think of it this way, is a linear combination of this special type of cuts. That is why these cuts only span the entire subspace C star. That's what we are claiming here. Now let's come to the verification of this equation, or at least understanding how it comes. So say this is our vertex set V1 and we have a partition V1 and this part is V2. So what is this set? This is the set of those edges in G, one end of which lies here and the other end lies here. That's it. That is just what E V1 comma V2 means. Okay. So, but on the other hand, to the right side of the equation, we see a sum like this, where we are considering the sum of these types of sets EV. That means the set of edges emanating from V, one single vertex. and by sum we again mean actually the sum in the vector space, that is symmetric difference. As the and the sum varies like this, varies over V1, as the vertex V varies over V1. So let us choose one V here. Say we call it V1 because we will have to consider another one. So then what is EV1? EV1 is precisely the set of those edges in the graph that are like this. Okay. So these are the edges. Some edges are there. This is E of V1. E of V1 is the set of these edges. Okay. Now, what we are saying is that xy, say xy is some particular edge. In place of x, you can think V1. And in place of y, say you think of another vertex V2. V2 also has some edges emanating from it. One of those edges is this edge V1, V2 itself. So that is why we are saying that each such edge xy lies in precisely two such cuts. In E of V1, this edge is in E of V1. Simultaneously, this edge is in E of V2 and not in E of any other vertex. Naturally, you can just simply see that. Okay. Now, when you will form this sum, of course, you are going to have this as a part of the sum, above sum. As you vary V, V will take the value V1 and V2. So you are going to, at some point, you are going to have to consider the sum EV1 plus EV2. What does that sum mean? It just simply means symmetric difference. That means you take all the edges in EV1, take all the edges in EV2, see whether they have any common edge, remove it. Whatever you are left with, they together will give you an edge set, and that edge set is the sum EV1 plus EV2. And you have to continue doing this process until all the vertices in V1 are exhausted. Okay. So that means our procedure demands what? That we remove this edge. Now the remaining edges form a set that is EV1 plus EV2. Now say you consider another vertex, V3. V3 may not be adjacent to V1 or V2, but in order to make matters non-trivial, say V3 is adjacent to V2 but not adjacent to V1. V3 also may have some other edges emanating from it, so that EV3 has this edge also along with these other edges, which also incidentally is an edge in EV2. Now in considering the sum of this entire thing, which is EV1 plus EV2 and EV3, this common edge has to be deleted. Okay, and like this the process will go. And I think I have drawn this rather incorrectly because I have drawn everything on this side. I forgot to take care of the fact that the other vertices should lie on that side, because we are considering, remember, we are not actually considering all this. So there I am a little wrong. We are actually not considering all the wait, I think I am missing something here. There is no problem in considering these star-like structures when I am considering EV1. Okay. No, I have not made a mistake. Yes, this is okay. The thing is that as we will have to we will have to consider all the edges, all the vertices in V1. So these other vertices that you see here that are also lying in V1, they will also be considered at some point in considering all the vertices. So when you, for example, consider this vertex, then it has its own E of V, and so this edge is going to be removed. This way you can clearly see that any edge, both of whose ends lie in V1 itself, are going to be removed. But what I have done wrong is not considering these situations. That is, there may be some vertices lying in V2, this capital V2 that will be adjacent to small v2. These edges will not be removed. And a similar thing will happen on this side also, naturally. So that is why only the edges that have their ends like this, one end lying on this side and the other end lying on that side, will remain. And that's how we will have this. Okay? And that is why these special types of cuts generate or span this subspace C star. Because I messed up a little in this explanation, so you also think of it carefully and see if I have still missed something further. Now this subspace C star has a name because it consists of cuts along with the empty set. Naturally, it's called the cut space. And the author continues, the subspace C star, which is more precisely C star of G, is, from the above proposition, is called the cut space of G. Is cut space a single word? No, I think they are two words. It is not difficult to find among the cuts E of V. We need not consider all of these sets because now these cuts only generate our cut space. An explicit basis for C star of G. Since the set of such E of V is a spanning set, in order to find a basis, you just have to remove vectors E of V from them so that you still have a spanning set, but you have the minimal number of elements. So that way that set will be linearly independent also, and hence it will be a basis. And thus to determine its dimension, which will be the number of elements in the basis, in any basis. I don't know why, but I feel like in this last part, in understanding that equation expressing E V1, V2 as a sum, still there is something that needs to be explained. I can't point my finger on it, but something is amiss. So that's why I am asking you to go through this very carefully and let me know if I have missed something. It's dimension which will be done in exercise 27. We haven't seen any exercises so far. That's because all the exercises appear at the end of this chapter itself, of which we are in one section. Not many more sections are left, so that's just it for tonight. In the next graph theory video, we are going to see some sorts of minimal cuts. They will be called bonds. Just like in the cycle space, we have vectors which are sums of cycles, and among them we have some minimal cycles, chordless cycles. So here also there are some minimal cuts in the cut space, and then we will see what properties they have. So that's it. For tonight I wrap things up, and tomorrow we have last Saturday we solved Gallian's group theory problems. So tomorrow let us solve Gallian's ring theory problems, that is problems on integral domain. That's what we are doing now. So see you tomorrow with Gallian's ring theory exercises and their solutions. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.